Hello everyone, hopefully you can see my screen just fine. Today, this will be the second how-to lecture in the OWPC series, which follows on quite nicely from yesterday's talk, which talks about how to safely work with phosphine gas, and this complements it well because this is kind of another surrogate phosphine gas which might be more available to most labs. So just to talk about tris-trimethylsilyl and some of its synthetic uses and applications. So as I mentioned, it's often referred to as a user-friendly phosphorus source and safer alternative to pH-3 gas. Because it is a kind of alternative, it's often referred to as a covalent synthon for the P3- anion, and you'll see in a second how that is used in synthesis. Because of this, it has a wide range of uses spanning ligand design, organophosphorus chemistry, and material science. But because it is such a dangerous chemical, this means that if you're trying to buy it commercially, at least from your go-to chemical vendors, then it's relatively expensive. And if you're using this as a starting material on a frequent basis, then this is probably not something you're going to be buying often. So we're going to have to consider ways to make this ourselves. Regarding some of the synthetic applications, then there's a few different methods. There's a whole range of examples that I've chosen a few. The first is that we can use tris-trimethylsilyl to prepare substituted phosphine. So in this case, we're having a nucleophilic phosphorus source, which allows us to use kind of easier to handle alkyl or aryl halides as our electrophiles. One kind of interesting area of research which has been kind of highlighted in some of the talks and posters is phosphobenzenes, and we can prepare these from these pyrrolium salts. We can also make phosphoalkenes, and we've just seen the chemistry that they can do, so obviously that's another exciting area here. And when we're talking about materials chemistry, then tris-trimethylsilyl and related compounds are often to prepare these binary metal phosphides. So these are often used as like quantum dots. And one of the benefits that's kind of not immediately obvious is that all of these are kind of homogeneous and solution state methods. So you don't have any metal byproducts. This is especially important when we go to this final one here. You start with completely soluble species and you're left with a solid. So you can see why tris-trimethylsilyl would be more beneficial than sodium phosphide, for example. Now, if you're looking at trying to make tris-trimethylsilyl, which is not something that everyone is going to do and very few people will do it, then there's obviously a few safety notes that we kind of have to consider first. So as you would imagine, tris-trimethylsilyl is a highly pyrophoric liquid, and it readily hydrolyzes to give a toxic phosphine gas. If you're trying to prepare this, as I've kind of outlined in this talk, then it will take up to a week, and you have to use very specialized equipment. So you have to plan well ahead to make sure that this is carried out safely. In addition, obviously, you would need to take fill out a risk assessment and ensure that appropriate fire safety precautions are in place. This does involve very advanced level Schlenk line techniques, so it's not something that I would suggest an undergraduate or master's student would really carry out, and with that in mind, we should always make sure that this is closely supervised at all times. Of course, it must be carried out in a clean fume hood, so I'd recommend removing all sources of water, flammable organic solvents and other chemical storage. And one thing that you can do to kind of improve the safety, or another preventative measure, is to line the whole fume hood with a metal tray which is filled with sand, so that can contain any glassware in the event of an accident and help prevent the spread of fire. Now, this is what you would need to prepare tris-trimethylsilyl. It's just funny to say it like this because it looks more like a recipe at this point, but you will need red phosphorus. This is our phosphorus source. Naphthalene acts as our soluble electron carrier. The solvent of choice is DME. This is 1,2-dimethoxyethane. Sodium is our reducing agent, and of course trimethylsilyl TMS chloride, sorry. And the theoretical yield for this is 200 grams. If you compare that with the unit price for a gram from Sigma Aldrich, and this will give you 32,000 euros of TMS phosphine. For these large-scale reactions, there's some lots of glassware and equipment that you would need. You'll need a large multi-neck round-bottom flask. For these scales, you will need an overhead mechanical stirrer. An air-free condenser is recommended but not essential. Again, a pressure equalizing dropping funnel is recommended but not essential. You will need a stir plate with heating mantle, a large filter for it, and of course dry sea light to aid in that filtration, suitably sized receiving Schlenk flasks, a distillation bridge, and finally for the storage of the trimethylsilyl phosphine, you'll need some sort of Teflon tap ampule. So this is what the initial reaction setup will look like before you even get going. As I mentioned, the mechanical overhead stirrer is necessary here because you have a lot of stuff in suspension the whole time. This probably isn't necessary if you're working on smaller scales, so anything less than 10 grams, you can probably get away with this just with a regular stir bar, but all of the additional things that I highlight today will still be relevant. A water-free condenser is nice here because it just avoids having additional tubing, which can make things a bit more complicated. And obviously, if we're working with very moisture sensitive compounds, it's just nice to know that there's no water even in close proximity to our reaction. The first thing we do is we load our flask with the pre-dried red phosphorus and naphthalene, and we purge the system with inert gas for a few hours. So you could technically just cycle this onto the Schlenk line as usual, but at least for the setup that we found in the Cowley group in Edinburgh, is even though that our multi-neck flask has a screw thread designed for the mechanical stirrer, it was airtight enough to allow this to be sufficiently protected under inert gas atmosphere, but not for it to be fully evacuated. And one thing you need to consider as well is that under vacuum naphthalene may sublime as well, so this avoids that problem as well. And you can just leave it under a gentle flow for a short while with a bleed needle to purge the reaction flask, and gentle stirring with the mechanical paddle just to agitate the solids. We then suspend the red phosphorus and dissolve the naphthalene in approximately 1.5 liters of DME. This will be, dependent on the size of the solvent ampules that you have, probably 1.5 of those. So again, like I mentioned, you need to do a lot of planning and preparation for this. This might require a few distillations or SPS collections a week before to ensure that everything's ready in time. Once we have our red phosphorus and naphthalene suspended, we heat that gently just to 40 degrees with stirring, and then we add the sodium slowly over the course of 2 to 3 hours. So you can just add this one chunk or half a chunk at a time through this opening here. And of course, you'll need to freshly cut the sodium prior to use to remove the oxide coating, and wash it with hexane to remove any residual mineral oil. Once we have added all of the sodium metal, we then cap this with a greased stopper and seal that. And then we heat the suspension to reflux, so approximately 100 degrees overnight or 16 plus hours. And in that time, the suspension will turn from a red color to black as we're forming sodium phosphide in situ. The following morning, we let this cool completely to room temperature, and whilst it's doing so, we can cycle a pressure equalizing dropping funnel onto the Schlenk line. And once we attach that to the reaction flask under a flow of inert gas, then we can then add our TMS chloride. We can add this either by syringe or cannula transfer it directly into the dropping funnel, and then we just add that at room temperature to the sodium phosphide suspension, again over the course of 2 to 3 hours, with strong stirring. You can also add the TMS chloride just by cannula transfer from a second Schlenk flask if that's what you prefer. Once all of the TMS chloride has been added, then the suspension will turn from a dark black to a light grey suspension. And then to ensure that all of the sodium phosphide is reacted with the TMS chloride, we again heat the suspension to reflux overnight at 100 degrees. If it looks like it's slightly too thick and doesn't stir too well after you've added all of the TMS chloride, then you can add some additional DME to help make this more mobile. The following morning, once this is all cooled back down to room temperature, the next step is to do the filtration. So this is kind of one of the trickier parts of the synthesis and one of the occasions where you might need more specialist glassware prepared specifically for this synthesis. And what we do is, like any salt metathesis reaction or many organometallic reagents, we will need to perform a filtration through sea light to remove the sodium chloride that's formed from the reaction. So here the filter for it looks very large, but this is probably to scale how big it is, at least the one in the Cowley group that we use. And essentially, it probably doesn't need to be this tall, but you want something as wide as possible to help speed up this filtration. And here I've shown a layer of sea light. If you're worried that during the transfer of this suspension to the filter frit that it might disturb the sea light level, then you can put a small bit of glass wool on top, and that will help prevent it being disturbed. To transfer this safely from the reaction flask into the filter cannula, into the filter frit, you will need the widest Teflon cannula that you can get. We use a 10mm diameter, so these are quite flexible, so it's quite easy to work with as well. And you may need to up the inert gas pressure during this process to enable the transfer into the filter frit. Once all of that has filtered, then you will then want to wash your solids and further extract the residual material. And you do this with several portions of DME. So you need approximately another 500 ml, so you can do maybe 2 or 3 portions. And it's good to add the DME directly to the reaction flask first, and that kind of rinses it out and makes the workup of this reaction flask easier later on. And we repeat that until we've completed the filtration. Following from that, we will then get a colourless or pale yellow solution. And the next thing is to obviously remove all of the solvent and remove the volatiles under vacuum. We're dealing with about 2 litres of solvent at this point, of a relatively high boiling solvent. So this will both take a long time and will require that you change the external trap periodically to ensure that this procedure is safe. Once we've removed all of the solvent and volatiles, then we're left with our crude product. And to purify it, we do a dynamic vacuum distillation. Because this is a relatively high boiling product, then it is suggested to have a distillation bridge with as few joints as possible. And because it is high boiling, there's no need to have essentially a cooling jacket on your condenser, because it will condense readily just with the ambient temperature. So before we do the distillation, it can be a good idea to heat the crude product under a vacuum just at 45 to 50 degrees for 15 to 30 minutes. This will help remove any residual TMS chloride, DME and naphthalene also. Once we've done that, we can cool our receiving flask in liquid nitrogen or a dry ice acetone bath, crank up the temperature and get the distillation to go. You may need to insulate your distillation flask with some foil and kind of encourage this along with a heat gun, because it's quite a oily liquid. Once the distillation is complete, we will want to let our distillation flask cool back down to room temperature, and we will want to let our receiving flask warm up to room temperature to let this fall. Once this does fall, we can then dismantle the distillation setup and cap this. and then we will want to transfer it to a Teflon tapped ampule for storage. And the best way to store this is in a fridge or freezer. It does freeze quite easily, but at least that way you know it's kind of more protected than a oily liquid, and then you will have to thaw it prior to use. Using this method, your typical yield will be between 60 and 80%, and if you do this, then I would imagine that the amount of TMS phosphine that you produce should last your lab months or years even. And the TMS phosphine is characterized by a high field shift at minus 250 ppm, which is quite similar to what you would observe for phosphine. Finally, the not so nice part of this chemistry is the large amount of quenching and cleanup that is necessary. Obviously, TMS phosphine is very pyrophoric, so we need to make sure that our quenching is done under a flow of inert gas. The way you do this is first dilute the reaction flasks and any equipment that we've used with hexane or toluene, and then we first add a dilute solution of an alcohol in one of these solvents, and then we up the concentration until we can confidently add the ethanol to that without there being any reaction. And then finally, we will want to add water and then bleach. As with many phosphines, they smell quite bad. So one of the ways you'll want to eliminate that smell is with bleach. So you may want to rinse or at least soak all of the glassware and equipment with bleach prior to your usual cleaning. And one thing that's also helpful either during the preparation of TMS phosphine or in later stages or later syntheses using TMS phosphine is to prepare a methanolic solution of iodine, which can also be used for quenching. And this kind of acts as an indicator to know when all of your phosphorus containing species have been oxidized. So when the purple brown color of iodine persists, you know that all of your phosphorus containing species are kind of safely quenched. With that, I would especially like to thank Clement and Rosie, their past and current postdocs in the Cowley group. It was Clement who actually did the synthesis and kind of gave me the method, which I've shared today. But this kind of is developed from Rosie's previous work in Bristol in the Russell group. And I imagine that this synthesis kind of is passed on from other academics, but I thought it'd be useful to kind of share today to the wider phosphorus community who will use this reagent more frequently. Finally, I'd like to thank the organisers for inviting me to speak today. And finally, thank you for your attention, and I'm happy to answer any questions that you may have.